A warm welcome to all the students for this lecture. In today's lecture, we're going to see what is an equivalence of NFA and DFA. We're going to prove today a very important theorem which says for any NFA M equal to Q sigma Q naught A and del, which is accepting any language L, okay, there is an equivalent DFA M1 equal to Q1 sigma Q1 A1 del 1 that also accepts the same language. In plain simple words, this means we are trying to prove that if there is an NFA that accepts a particular language, then there exists an equivalent DFA that also accepts that same language. Okay. Now, to prove this particular theorem, we're going to make use of some mathematical concepts that we saw in our prerequisite lectures. For example, a principle of mathematical induction and so on. So without wasting time, let us begin how to solve. So since what is asked, we are asked to prove that there is an equivalent DFA. So using proof by construction, I say that let M1 equal to Q1 sigma Q1 A1 and del 1 be the resultant DFA such that what will be the individual parts of this DFA? Okay, so Q1 will be subset of 2 raised to Q. Okay, now by writing this I simply mean that although Q1 are nothing but set of states in the DFA, these states will be subset of all the possible states which are there in the NFA that we already have. 2 raised to Q possible states are there in NFA. So the set of states in DFA will be subset of the set of states possible in NFA. That is the meaning of it. So I will just name this as equation 1. Further, we always assume that the initial state of NFA and that of DFA is same. So in this case, the DFA's initial state is Q1. I am saying that this initial state of DFA is same as the initial state of NFA, that is Q0. Okay, this is our second assumption, that the initial state of NFA and DFA will be the same. This is second assumption. Talking about the set of final states, okay, I write A1, that is set of final states, will contain state Q belonging to capital Q1, where or such that each of this state intersection with A, that is set of states in NFA, not equal to null. Okay, I will just talk about this. So this is equation 3. Okay, what is A1? A1 is set of final states in DFA. Now, so Q, each state Q in that set of final state will be such that, okay, Q intersection A. Now what is A? Each set of final state is NFA, right? Q intersection A is not equal to null. That means there will be something common among the set of final states in NFA and one of or each of the state in DFA. That means by writing this, I am saying that, okay, the set of final states in my DFA, okay, might have something in common with the set of states in the NFA. So they are not disjoint. That's the meaning of it. And how the transition function is defined? Transition function is written as del 1 of a particular state Q on reading A will be given as union of, I am just writing a recursive definition, R belong to Q into del of R comma A. So this is just a definition of transition function of D of A recursive definition. So this is, I'll just call this as equation 4. Okay. So I have assumed that M1 is the resultant D of A. The set of states, the set of finite number of states Q1 is a subset of 2 raised to Q. That's the total number of states in NFA. Start state of the resultant DFA is same as the start state of the already existing NFA. Then we have also considered these two results, and now let us start. Now what is asked to prove? It is asked to prove that there is an NFA which accepts a particular language. Okay, then there is an equivalent DFA that also accepts that same language. I can say that if NFA, if M1 is the NFA, or sorry, if M is the NFA, and if M1 is the resultant DFA, I can say that NFA and DFA are equivalent if all the strings that are accepted, all the strings in general X that are accepted by NFA should be also accepted by DFA. And all those strings X which are rejected by NFA should be also rejected by DFA. So if DFA accepts all those strings or all those languages that are accepted by NFA, and it rejects all those strings which are rejected by NFA, okay, then I can say that NFA and DFA, they are equivalent to each other. Okay. So now how to establish this fact? We will make use of extended transition function. Okay. In general, when we discussed extended transition function, what did we say? What is the meaning of extended transition function? Okay. So from a particular state Q, okay, extended transition function tells you whether a given input string is accepted or whether the input string is rejected. So the end result of this extended transition function is either accepted or it is rejected. And it tells whether the string is accepted or it is rejected based on the set of states that are obtained at the end. We have seen already in the previous lecture. Okay. Now, so what is the meaning of acceptance by DFA? Okay. So now since M1 is the DFA that we have considered, and in this M1 DFA we have Q1 sigma, Q1 A1 and del 1. These are the tuples in the DFA. Okay. Let us establish what is the meaning of acceptance by DFA in this regard. Okay. So extended transition function for the DFA will be del 1 star. From the start state Q1, on reading the input value X, okay, the extended transition function of DFA now will tell whether this string is either it is accepted or rejected. So this is extended transition function for the DFA M1. Fine. So this is the extended transition function for DFA. Now we already have a NFA M whose tuple values are Q, sigma, Q naught, A and del. So let us see how extended transition function for NFA is written. Extended transition function for NFA will be del star from start state Q naught. X is given as input. So again this extended transition function of NFA, okay, after taking X as input will tell you whether the string is accepted or rejected. Okay, so now extended transition function of DFA after taking a string X tells you whether this X is accepted or rejected. Extended transition function of NFA after taking this input string X tells you whether the string is accepted or rejected. And now if you consider this fact, NFA should accept all the strings that are accepted by DFA, or in general DFA, if it is able to accept all strings that are accepted by NFA, and if it is able to reject all the strings which are rejected by DFA. So if this is accepted, if string X is accepted by DFA, it should be also accepted by NFA. If string X is rejected by DFA, the same string X should be also rejected by DFA. So in general, if the extended transition function for DFA on reading X is equivalent to the extended transition function for NFA on reading the same input X if we are able to prove this equivalence. Okay, it is sufficient for us to prove that for an existent NFA there is an equivalent DFA. And it is this particular fact that we are going to utilize in the proof that we are currently solving. Okay, so we will utilize this particular relation, and let us continue with the proof. M1, that is my DFA, M1 accepts the same string X belonging to a particular language L, okay, that is already accepted by NFA M, okay, is true if we are able to show, that del 1 star, so this is extended transition function for DFA, from the start symbol Q1 reading X gives you the same result that is given by the extended transition function for NFA, that is del star, from the start symbol Q0 on reading the same input symbol X. Okay, so if we are able to show that del 1 star Q1 comma X is equal to del star Q0 comma X, where del 1 star is an extended transition function for DFA, del star is extended transition function for NFA, Q1 is a start state of the DFA, Q0 is a start state of an NFA. If we are able to show that extended transition function on accepting the same input string, on taking as input the same input string from the same language, if both the extended transition functions, if both of them either only reject that string or both of them if accept that particular string, then we say that this DFA is equivalent to this NFA, or in general we say that this NFA has an equivalent DFA, that is this. So we need to prove this. Now this can be proved. This can be proved actually using various ways, but here I will try to prove this using structural induction, mathematical induction on X. So we have to prove this. Okay, now let's start with the minimum possible value of X. So for X equal to null, we need to prove del 1 star of Q1 on null is equal to del star of Q0 on null. We have to prove this, where I've just substituted X with its minimum value, that is null. So we have to prove this initial result. So consider the left hand side, that is consider del 1 star Q1 on null. Consider this. So looking at the definition of extended transition function of DFA, it is very clear that del star of any state Q1 reading null gives you that state Q itself. So applying that over here, I can say del 1 star of Q1 comma null is equal to Q1. How I have got this? Using the definition of extended transition function for DFA. Now we have got Q1. Looking at the definition of Q1, okay, I just told you initially that the start state of the resultant DFA will be equal to the start state of NFA. So Q1, that's a start state of DFA, can be also written as Q0. So I will utilize this equation too, and I will by saying that Q1 can be written as Q0. Okay, using equation 2. Okay, now my aim is to get what? From this left hand side, I have to somehow get this del star Q0 null. Now this can be further written as, now Q0, again using extended transition function of NFA, I can write Q0 as how? Del star, okay, of Q0 on null. So this is using del star for NFA. Okay, so del star of any state on reading null gives you that state itself. So reverse way, Q0 can be written using the del star of NFA as this. So we started with the left hand side. Have we got the right hand side? Yes. So this is equal to right hand side. Okay, since left hand side equal to right hand side, okay, the result is proved for x equal to null. So for minimum value of x. Now we will assume the result is true for some x. So induction hypothesis. So for the value of string at some x, we'll assume that del 1 star of q1 comma x is equal to del star of q0 comma x. We'll assume that this result is true. Okay, so this is our induction hypothesis. Okay, and now we have to prove that for some string say xa that is greater than x, we have to prove del 1 star of q1 comma xa is equal to del star of q0 comma xa. So this induction hypothesis, I will just name it as a particular equation, say equation 5. So we have to prove this result, del 1 star of q1 comma xa should be equal to del star q0 comma xa. If we are able to prove this, okay, our theorem is proved. Now consider the left hand side. Okay, left hand side of what we are asked to prove, that is del 1 star of q1 comma xa. This is the left hand side. Now how can we proceed? So this can be written, now since this is DFA, can we use the non-recursive definition of extended transition function of DFA? So del 1 star of q1 comma xa can be then written as del 1 of del 1 star of q1 comma x comma a. And how I have written this? This is the definition of extended transition function for DFA. Okay, this is non-recursive definition of DFA that we had already seen. Now you see this part. Okay, when you consider this part and compare the induction hypothesis that we have, in the induction hypothesis we have assumed the result to be true. The result is del 1 star of q1 comma x is equal to del star of q0 comma x. So wherever del 1 star of q1 comma x is there, I can easily replace it with del star q0 comma x. So using this equation 5, that is induction hypothesis, I can now write this result as del 1. So this can be written as now del star of q0 comma x comma a. So how we have done this? Using equation 5, that is induction hypothesis. Okay, and finally what you see here, now please note, when extended transition function is not there, and when we are talking about a symbol transition function, whether it is del 1 or whether it is del, it is same. Only when I write del 1 star is not same as del star. But when you are talking about simple transition, del 1 and del, they are same. Okay, so you may interchangeably write del 1 or del. So looking at this in turn, okay, can be converted to del star. Okay, this can be converted to del star of q0 comma xa. And how we have done this? This is using the non-recursive definition. Using the non-recursive definition of NFA. Okay, so actually del star of q0 comma xa can be also written as del of del star of q0 comma x comma a. So this is using the non-recursive definition of NFA. So as a result, the left hand side is now equal to the right hand side. Hence, we have proved that for any NFA accepting a language L, there exists an equivalent DFA. So this is how we have proved. So that is it for today's lecture. In my next lecture, we will solve some problems and we will see a construction technique called as subset construction technique, and we will solve problem that can convert a given NFA to DFA.